Welcome. This is Chapter 2, Section 1, Represent Relations and Functions. Start off with, as usual, with vocabulary. Vocabulary for a relation is any, we'll say set of ordered pairs. Any set of ordered pairs. Basically, it maps an input with an output. Oops. All right, domain are all of the input values. Usually it's the x's. The range is the output values. And typically it's the y's. Now something is a function if the input always maps to the same output. So what that means is I can have a bunch of ordered pairs here. Okay, I can put 1, 2, 3, 1. Now it doesn't matter what the outputs are. Okay, this can be a 0, this can be a 4, this can be a -2. If for some reason you see another 1 here, for this to be a function, it has to map or match to the same output. So here's a 1, here's a 1. It needs to map to a 0. For this to be a function, it has to have a 0 there. An equation in two variables is exactly the way it sounds. It's a mathematical sentence. It's a mathematical sentence that have two different, has an input and an output and y. So has an independent and dependent variable. I'm just going to write equation with two variables. A linear function. A linear function comes in this form. A linear function basically is just that. M and B are constants. So if I wrote an equation y equals 2x plus 3, that's linear. Y equals 3x minus 5, that's linear. As soon as you put an exponent like that, not linear. As soon as I say a variable in the denominator, not linear. All right, let's check this out now. Oh. So, representing relations. A relation can be represented in the following ways. Ordered pairs. Those ordered pairs can be rewritten into a table, -2, 2, -2, -2, 0, 1, and 3, 1. They can be shown as a graph and as a mapping diagram. Now, one thing I want to point out with the definition. All of these are relations, but is it a function? So we look. If the inputs, so here's the input, always maps to the same output. So 3 goes to 1, 0 goes to 1. It doesn't matter that these numbers repeat. It only matters if these numbers here repeat. So if negative 2 goes to negative 2, then that means negative 2 here has to go to negative 2. Since it does not, this is not a function. If you look at the graph, you can tell. And if you look at the mapping diagram, you can see how that works. So, example number 1 from your note-taking guide. Tell whether each relation is a function, and then explain. So, the question is, does each input always go to the same output? Negative 2 to negative 1. That means anytime negative 2 shows up, negative 1 should be its answer. Negative 1, 0, 3, 0, 6, 4. The relation for A is a function because each input is mapped onto one output. Please notice that the outputs can repeat. The inputs should not. So, part B, negative 2 goes to negative 2. 1 goes to 0. 2 goes to 2. If 2 goes to 2, then 2 should always go to 2. But since there is a problem right here, that means the relation is not a function because the input is mapped, because the input of 2 is mapped onto both 2 and 3. So you can do that just by looking at ordered pairs. You can do that by looking at mapping. You could graph it. You could do a lot of ways here. So for the checkpoint, is the relation given by the ordered pair here a function? So you could do mapping if you wanted. Negative 5, negative 3, 0. That's the input. The range is 2, negative 1, 0, 5. Let's talk about this. Negative 5 goes to 2. Negative 3 goes to negative 1. 0 goes to 0. 0 goes to 2. 0 goes to 5. And you should see that since 0 has 3 different possible outcomes, this is not a function. Guided practice number 1. It's just like, here, this is on page 73. It gives a set of ordered pairs. And inside the ordered pairs, the input, the x's are negative 4, negative 2, 0, 1, and negative 2 repeats. So if a number repeats, you don't write it twice. That's the input. Outputs. Three, 1, 3 repeats. Negative 2, negative 4. So the question is, here are the inputs, there's the outputs. What are the, is this a function? Well, negative 4 goes to 3. Negative 2 goes to 1. 0 goes to, oops. 0 goes to 3. 1 goes to negative 2. Negative 2 goes to negative 4. So, the fact that the 3 has 2 arrows is no big deal. That's an output. Those can repeat. It's this negative 2 that has 2 outputs that is a problem. So you say not function. You can use mapping, or you can use something called the vertical line test. The vertical line test shows a relation is a function if and only if no vertical line intersects the graph of the relation at more than 1 point. So you basically graph it and test. So here's the graph. Is there anywhere a vertical line will pass through that line twice? If the vertical line test, VLT, checks out, it's a function. As soon as you have one place that's a problem, vertical line test, fail, it's not a function. Use the vertical line test. All right, so here are some points. This graph does represent a function because no vertical line intersects the graph at more than 1 point. Right here, one vertical line. Here, all you need is one example where it crosses twice, 2 times. Once it crosses once, this graph is not representing a function because a vertical line at x equals 3 and 6 intersect the graph at more than 1 point. I just take a look at the guided practice number 3 talks about example 3. Suppose that Kevin Garnett averages 24.2 points per game in his 10th season, as he did in his 9th. If the relationship given by the second graph is revised to include the 10th season, is the relation still a function? So you're looking at average points, and you're looking at how old he is. So you're adding another year to his time. And what that does is it doesn't add extra points. You just add that point so that it doesn't count. And so number 3, basically you're going to have a bunch of points. Okay, vertical line test passes. If you add a point, as long as the vertical line test passes, then you say it's still a function. If we had added another point here somehow, then you'd have problems. All right. Graphing equations in 2 variables. Construct a table of values. Plot enough points from the table to recognize a pattern. And then connect the points with a line or curve. And the curve part is very important because this works for all graphs. So you could go and you could graph any type of equation you wanted as long as you constructed a table of values, plotted enough points from the table to recognize a pattern, and then to connect the points with a line or a curve. So let's take a look at this example. Step 1, construct a table of values. You put -2 into that equation. Why don't you pause the video, and when you unpause, you'll see all the points. So you should have seen these. You should have gotten these points. You should go ahead and plot the points, and then notice that they all lie on a line. Okay, so plot those points. I'm sorry, pause the video and plot the points. So there's their line. You should see that the pattern would continue like that. Draw as straight a line as you can. And then I guess you would say draw the points with a line. So, tell whether it's a function or not. Well, it's a function if it's in mx plus b form. There's no exponents, the variables aren't in the denominator. Right here, this is the function f is a function. Oh, no, I'm sorry, is linear. Sorry. It's linear if it doesn't have any of the x in the denominator and exponent and stuff like that. So, because it's in this form. So now, when you solve this, it says let x equal -3. So here's an x, and I just said that x is -3. So here's an x, it should be -3. So you substitute -3 in for all of the x's, and now you should have as an answer f of -3 equals -8. So the function g is non-linear because of the x squared term. That doesn't mean you can't plug in -3 though, it just means you plug it in maybe more than once. So once you substitute -3 in for x, once you pause the video and try to do that order of operations, you end up with 5. Alright, let's get moving here so we can finish this under 20 minutes, maybe. Check, complete the following exercise. Use the vertical line test, the VLT, to tell whether the function is a relation. So look, oops, there should be no way to draw a vertical line through those points. So here's a vertical line. I move the vertical line along, and at no point does it cross more than once. So is this a function? Yes. Graph this. All right, we need a table. 0, 1. Put 0 in for x. Well, if you put 0 in for x, your answer is -3. If you put 1 in there, it becomes -1. So 0, -3, 1, -1. You've got 2 points. You can draw a straight line. Tell whether the function is linear, then evaluate the function when x equals -1. All right, tell whether it's linear. That means no exponents on the variables. It means no variables in the denominator. So right away, you know this is non-linear. And then plug it in. 2 times -1 cubed. That's right here. Linear. Go ahead and pause the video and try to finish it up. All right, so this one here, see it's 2 times -1, that's -2 plus 6 plus 1. That should give us 4 plus 1 gives us 5. Right here, that's -4 plus 9, that's 5. So both of these end up with a solution of 5. All right, let's keep going. Guided practice 4. All right, 2 more problems here. We should be good to go. So guided practice 4, graph the equation. So to start off here, again, you need an xy. You may want to go back here to the steps and add something in here. Put in here for step 2 that linear only need 2 points. If you know you have a linear equation, you only need to have 2 points. So for us, number 4, The equation is 3x minus 2. So we only need 2 points. So 3 times 0 minus 2, that means negative 2. 3 times 1 minus 2, 1. And then a wonderfully drawn set or coordinate plane, 0, negative 2, 1, 1. Draw your straight line. You should be good to go. Number 6 is tell whether it's linear or not. This is number 6 on the guided practices. You see there are no weird exponents, no denominators that are ugly. So this is linear. It says what is it when x is negative 2? So that means g of this x becomes negative 2. Negative 4 minus 2 times negative 2. Negative 4 minus, negative 2 times negative 2 is plus 4. You should end up with 0 as your solution. I tried to keep this as close to 20 minutes as I could. These are the problems that we'll do in class. Make sure to finish your guided practices, and we'll see you.